In this lesson, we'll try to see what is Varignon principle and how it is used to find the resultant of a system of forces. To begin with, we'll consider the situation of two parallel forces F1 and F2, which are acting at distances x1 and x2 from y-axis as shown. It was discussed in the previous class that the resultant of these two forces will have a magnitude which is sum of the forces, and it acts at a distance x is equal to f1 x1 plus f2 x2 over f1 plus f2 and is parallel to both the forces. In fact, thinking along the same lines, we can extend it to any number of forces. That is, on the same object, let us say if you have forces F1, F2, F3 and so on up to Fn, they are acting at distances of x1, x2, x3, so on up to xn. Then you can say that the resultant of all these parallel forces is equal to sum of F1 plus F2 plus F3 and so on. And the distance at which the resultant R acts is given by a similar relation but including more terms, F1 x1, F2 x2, so on up to Fn xn. Okay. Once we note this, notice that the denominator here is the magnitude of the resultant R. So we can take this R onto the other side and write Rx is equal to F1 x1 plus F2 x2 plus so on up to Fn xn. Okay. Notice the units of the quantities. This R has the units of Newton, this X has the unit of meter. So this Rx has the unit of Newton meter. Similarly, this has the unit of Newton meter. This has the unit of Newton meter, and so on. We recall from our earlier discussion that a fundamental quantity which has Newton meter as the unit is moment of a force. Okay. Moment of a force is, in some sense, force has a tendency to rotate an object, and that tendency of the force to rotate an object is called moment. It depends on the magnitude of the force, newtons, and it also depends upon at what distance it is acting. Okay. So this can be summarized in the form of a statement: moment of the resultant, this is the moment of the resultant, is equal to the sum of moments of the forces. This is the moment of one force, this is the moment of another force, and so on. So moment of the resultant is the sum of the moments of the forces. Okay. This principle is called Varignon's principle. Varignon's principle or Varignon's theorem. Okay. This theorem we have shown for a situation where all the forces are parallel and all the forces are acting in the same downward direction. But it can be shown that this theorem is true in a general case where the forces are meeting at a point, or not all the forces are meeting at a point. This theorem can be used to find the resultant of forces in a general case. That general case is shown here. In this case, you have an object with a number of forces F1, F2, F3, F4, F5, and so on. Some of these forces are parallel, some of these forces are not parallel, and not all of them are meeting at 1 point. In such a general case, to find the resultant, we follow a 3-step procedure. In step 1, we try to find the magnitude of the force. That magnitude is given by finding, magnitude is obtained by finding the x component of the resultant Rx bar, which is the sum of components of the forces. F1x is the x component of force F1, F2x is the x component of force F2, and so on. Similarly, the y component of the resultant is given by F1y plus F2y, and so on. All these are y components of individual forces. Once you obtain this Rx and Ry, you can find what is the magnitude of the force by summing the squares and taking square root. So thus you find what is the magnitude. The next thing you need to find is the quadrant in which this resultant R lies. We know that if both x component and y component are positive, it lies in first quadrant. In the second quadrant, you have x component negative, y component positive. In the third quadrant, you have x component negative, y component negative. In the fourth quadrant, you have x component positive, y component negative. So depending on the signs of Rx and Ry, if Rx and Ry are both positive, you will say that R lies in first quadrant. If Rx and Ry are both, if Rx is positive, if Rx is negative and Ry is positive, you say it lies in second quadrant. If both of them are negative, it lies in third quadrant. If Rx is positive and Ry is negative, it lies in fourth quadrant. So you can find out the quadrant in which the resultant lies by using these observations. And also the angle the resultant makes with the x-axis, that is theta, you can find as tan inverse Ry over Rx. While computing this tan inverse, you will take absolute values of Ry and Rx because the quadrant is already decided. So the next thing that remains to be done is to find where is the location of the object. For that, let us say your resultant is somewhat like this. Okay, let us say your resultant is lying in, let us say, fourth quadrant, and its line of action is shown. Okay, let us say this distance, if you draw a perpendicular from here to here, and let us say this angle is 90 degrees, and let us say the length of this perpendicular is L, then the moment of the resultant is R times L with appropriate sign. In this case, when you take moments about point O, the sign of RL moment is negative because it's clockwise. Okay, so you try to sum up the moments of the individual forces F1, X1 plus F2, F3 and so on, and equate it to RL. We know the magnitude R, we know all these quantities F1, X1, F2, X2, F3, X3 and so on. Thus we know where is the location L. Once we know the location L, we can also notice if you try to extend it further and try to extend this force also further, we know this angle theta, which is this angle theta, and if you assume these to be OAB, in triangle OAB, sin theta is L over OB, let us say this is L over X. No, we cannot use X. L over, let us say XP, to indicate that it is a point of intersection where this resultant intersects with x-axis. Thus you can find xp to be L over sine theta. So we found the magnitude, we found the quadrant in which it lies, and also we found the point of intersection of the force with x-axis. Thus the resultant R is completely defined. We'll try to see one or two examples on how to find the resultant using a couple of problems.